Welcome back to All This Math. See, I still got my order of operations hoodie on. This next lesson, we're going to talk about similar polygons. Now, what are similar polygons? Similar polygons are basically shapes that are polygons that have the same angles, but basically one is a bigger version of the other, right? So that means that each side was expanded by the same rate or by the same ratio, right? So it's like a parent and a child. Like you got like a mini me and an older version, right? That's what similar polygons are. But the thing you got to remember about similar polygons is that the angles stay the same. The angles are the same. It's just the sides get longer. So if you look at these two are similar polygons, so you can tell that this is a smaller version of this. That's all it is. This is a smaller version of this. And every side, the relationship between what we call corresponding sides, so like the top, right? CD, segment CD, corresponds to the top on this one, segment GH. So if this is 6 and this is 12, this is half of this. So that means the corresponding side to BC, the left side, the left vertical side, would be FG. So we don't know what FG is, and it's not labeled, and nobody asked us what FG was, but we can tell that because these are similar polygons, and 6 is half of 12, then we say, okay, well, I know my multiplication facts. I know 4 is half of 8, so FG would have to be 8. Likewise, EF would have to be 6. How do I know it's 6? Because AB corresponds to EF, or AB matches up with EF, and AB is 3, and that's half of this. So even though it don't look like it, really don't look like it, but it's not to scale. That's what that's called. When the picture the picture doesn't reflect the actual numerical characteristics of it, we say that's not to scale. But don't trust what it looks like necessarily. Always trust what the information you're given about it is. So if this is 3, this is half of this. So this has got to be 6. And if this is 8, this is half of this. So so EH got to be 16. All right. So now, but what we're doing in this particular problem is this. We're given 5 statements, A, B, C, D, and E. Hopefully you can read that, right? And we're asked, are they true? Which ones are true? So we're going to label the ones that are true. We're going to label the ones that are false, all right? So let's read the first one. It says segment EF is twice as long as segment AB. So let's look at EF. EF is right here. And it says this is twice as long as segment AB. And we actually already talked about that. I gave it away. So we're going to say, yes, I'm going to check off the ones that are true. So that's true, right? Because they're similar polygons. Now, how do I know it's twice as long? Because I already know that this is 6 and this is 12. So if GH basically is twice as long as CD, then that means that EF got to also be twice as long as AB, right? That's kind of like, that's the logic that we use when we're doing geometry, right? If this information we know, then we can figure out other information and other relationships between other things. And that's why like math is relevant, because that's life. Like you need to figure things out in life at all times. All the time, you constantly need to figure things out. So you need to be able to know how to take some information that you already are aware of, something that you're looking right at in front of you, and say, okay, well, if this is related to this way, then this other thing over here should be related to this other thing over here in the same way. All right. So that's another example of how we can use math to train our brains to think critically in certain situations. So that's one of the answers to the question when you ask your teacher, when am I going to use this stuff? Why I got to learn this? Because it trains you how to think and how to think critically. And if you're a person that can think critically, especially in America, then you'll probably get along much further than a person that does not know how to think critically. All right. Now let's go to statement B. Statement B, segment CD is twice as long as segment FG. Where's BD at? No, CD. CD is right here. And it says CD is twice as long as FG. Not at all. Not at all. Because FG is actually twice as long as CD. So this is not true. All right, they're trying to throw us for one. All right, so I'm going to put an X through that. All right, again, this is the bigger polygon. This is the smaller polygon. Bigger, smaller, bigger, smaller. And there's a scale ratio, we call a scale factor or scale ratio. of 2 to 1, meaning that every side in this polygon is double the length of its corresponding side, or the side that it matches up with, right? The top matches up with the top. The left matches up with the left. The bottom matches up with the bottom. The slanted right side matches up with the slanted right side, all right? Now, choice C, the measure of angle, that's an angle symbol too, of angle HEF is twice the measure of angle DAB. So again, this is something else you got to just memorize about similar polygons. When we're dealing with similar polygons, the angles are always congruent. The angles don't change. The sides may be double of each other, but the angles are going to be consistently the same. The angles are going to be the same. So this angle matches up with this angle. They're congruent. This angle matches up with this angle. B with F, they're congruent. C with G, they're congruent. D with H, they're congruent. Again, A with E, they're congruent. Angles are going to be congruent. So this is wrong. All right, so memorize that about the angles, okay? Choice D, the length of segment EH is 16 units. First of all, where is EH at? EH is in the big polygon. It goes from point E to point H. That's this right here. We don't know what it is. It's not labeled, but we do know the corresponding side in the smaller polygon is AD, and AD is 8. So if AD is 8, and we already know that this polygon is twice as big as this one, how do we know that? Because we knew that this side was 12 and this side was 6, and 12 is double of 6. And the same relationship is going to be maintained through every pair of corresponding sides. Every pair of corresponding sides. So if 6 times 2 gives me 12, then 8 times 2 is going to give me 16. So EH is 16. So that's true, 16 units. All right, last but not least, statement letter E. The area of EFGH is twice the area of ABCD. So that's also going to be true because the amount of space inside is going to be doubled because the lengths of the sides are going to be doubled. All right. Now, this is not a rectangle or a square, so we can't just multiply the length by the width. This is what we consider, I think it's called an oblique shape. I should know that, but I think it's called an oblique shape. But anyway, if we think about what the definition of area is how many little 1 by 1, whether it be 1 inch by 1 inch, 1 centimeter by 1 centimeter, 1 mile by mile, 1 mile, whatever the unit is, how many of those units can fit inside of the shape or inside of the polygon. All right. So if the width or the length of, let's say the length of this doubles and the length of every one of the sides doubles, then that means that the amount of space inside must double also. It must double also. Okay? So this is going to be true. So this is also going to be true. Choice E. All right? All right? And that's just a little bit of exercise with similar polygons. Okay? So this is really just an exercise in having you memorize the rules of similar polygons, some of the background information about them. But, you kind of just got to see these rules over and over again. The relationships between the angles. Remember that the angles don't double. The angles don't change. The angles in similar polygons are going to be congruent. They're going to be the same. The corresponding angles are going to be the same. But you figure out what the scale factor is. So in this case, the scale factor is 2, right? Because this polygon is double the size of this one because 12 is double of 6. All right. But yeah, you just got to just memorize those rules about similar polygons. All right. And just do a bunch of problems until you commit it to memory and then you master it. All right. So go get some practice, do some more work with similar polygons, and I'll catch up with you on the next video. All right. Peace. All right. Look, I thought I was finished with this video and I thought I was finished with this lesson, but I'm back because I got something to talk about. I was tripping. I made a mistake. And I know somebody probably watched this video up to the part right before this, and they probably saw like, what's he talking about? Like, how is the area of EFGH twice the area of ABCD? How is that true? This is not true. I initially said it was true, but I made a mistake. It happens to the best of us. Now because I had to think about it after I stopped the video. I thought about it for a minute, and I was like, nah, that don't sound right. Because I know if you double the length of the sides then the perimeter will double. That's straight up. The perimeter will double, right? Because if each of these numbers double, then the perimeter is going to double, because the perimeter is just the result or the sum of all the sides added together anyway. So if this becomes a 12, this becomes an 8, this becomes a 6, this becomes a 16, then the original perimeter is going to double. But with the area, with the space inside, it sounds good, but even when I was saying it, it didn't really make sense, right? I should have looked more deeply into this before I hit record the first time, right? And I was going over this problem before I did the video. But anyway, I'm fixing it now, you know, to try to fix my errors. Think about it like this. I'll give you an example of why this is not true. The area of EFGH is twice the area of ABCD. We know that the sides double in length, right? But what if we had like a square, right? Let's say we had a square. Square is 2 by 2, all right? Let's say we double that square. Now the square is 4 by 4. Now area is length times width. So the area of this square is 4. But the area of the big square is 16. So look at that. Compare 4 to 16. 4 is not half of 16, and 16 is not double of 4. So that's like a way to prove that this is actually not true. So that's actually not true. The area of EFGH is not twice the area of ABCD. When we have like scale drawings or similar polygons, when the lengths of the sides change, whether they double, triple, whatever, the area is going to do something different, because the area expands exponentially. Area actually expands exponentially. Only the perimeter will have the same relationship as the scale factor. All right. So if the sides double, then the perimeter doubles. But the area is going to grow exponentially, depending upon what the relationship is between the original shape or the smaller shape and the bigger shape. All right. So I just wanted to add that. Just wanted to add that. So just keep that in mind. All right. See, professors, teachers, we make mistakes too. All right. See you on the next video. Peace.